All right, so welcome everyone to the Schubert seminar. Today we're happy to have Brendon Rhoades from UC San Diego telling us about equivariant cohomology and orbit harmonics. Please take it away, Brendon.
All right. Well, thank you very much. I am honored to be given the opportunity to speak in this esteemed online seminar. And the work I'll be talking about today is joint with my postdoc, Raymond Chou at UC San Diego, and Tomoo Matsumura at ICU. And I guess Tomoo is in on this Zoom call. Right. The title of the talk, I guess, contains two objects, equivariant cohomology and orbit harmonics. So equivariant cohomology, this is an object that arises in, say, topology or algebra cohomology theory, where you don't just have spaces, you have spaces with group actions, and you want to take these group actions into account somehow. And then we have orbit harmonics, and orbit harmonics is this machine in combinatorial deformation theory, where you basically start with a locus of points in affine space, and out pops a graded ring. A lot of the graded rings that we know and love in algebraic combinatorics can be shown to arise from this method. For me at least, orbit harmonics is something that I've been kind of looking at quite a bit in my research in the past few years. It's something I really kind of know and love and advocate for. Equivariant cohomology is a little bit newer, and I guess I'm aware that for maybe many people in the audience, it's the other way around. Yeah, sort of for that reason, I'm very happy to give this talk. This talk is going to go over sort of a, to me at least, mysterious connection between these two objects. And if someone in the audience can shed some light on that connection, that would be just terrific. Okay, so, oh wait, whoa. Okay, outline. We're going to start just very classically. We're going to talk about and perhaps review the Borel presentation of the cohomology ring of the flag variety in type A. And when I talk about cohomology, by the way, I'm always going to work with complex coefficients just to make my life easier, although much of what I say can be generalized to integer coefficients just fine. So we're going to be talking about the cohomology of the flag variety and also its equivariant version, the torus-equivariant version. Then we're going to discuss this orbit harmonics deformation. And then we're going to enter a section of the talk that I'm referring to as just phenomenology, this sort of mysterious thing where orbit harmonics can somehow predict Borel-style presentations of equivariant cohomology from Borel-style presentations of ordinary cohomology. So we'll kind of see how that works. So we're going to begin with symmetric polynomials. So I guess I've said it in other talks, but let it be known, this is my favorite group action. The action of the symmetric group Sn on the polynomial ring and in variables, say over the complex numbers, where I permute subscripts like this. And usually it's in a Galois theory class that we finally get to teach our students about symmetric polynomials. So if I have a polynomial and in variables that's left invariant under any possible permutation of the variables, that polynomial is called symmetric. Symmetric polynomials form a ring. This is a graded ring. It's graded C algebra. And at least we like to say that the structure of this graded C algebra was determined by Isaac Newton, right? Usually the one symmetric polynomial that we teach in that Galois theory course is the elementary symmetric polynomial that looks like this, the sum of all square-free monomials of degree d. And Newton proved that the ring of symmetric polynomials, this invariant ring, is itself a polynomial ring, but it doesn't have in generators of degree 1 anymore. It's generated by E1, E2 up through En, these elementary symmetric polynomials, and these polynomials are algebraically independent. Okay, so these are symmetric polynomials, and really, what we're interested in is somehow a dual object. And the way I usually teach this, when I teach a graduate course in combinatorics, is I say that as mathematicians, symmetric polynomials are very interesting objects, right? However, if you were the symmetric group, a symmetric polynomial is quite boring, right? You can't change a symmetric polynomial by permuting variables. So we have this representation, a symmetric group acting on a polynomial ring. This representation has a boring part. And if we get rid of the boring part, maybe we're left with something interesting. And this leads to this notion of the co-invariant ring. So what does it mean to get rid of the boring part? It means you mod out by an ideal. The relevant ideal in this case, well, morally, it's the ideal generated by symmetric polynomials. Of course, constant polynomials are symmetric. We don't want to include those. So this little plus sign means I'm only thinking about things of positive homogeneous degree. And explicitly, you can think about this ideal as being generated by E1, E2 up through En by Newton's theorem. So the coinvariant ring, the type A coinvariant ring, is the quotient of the polynomial ring in invariables by this coinvariant ideal In. And what kind of an object is this? Well, I guess I have a homogeneous ideal. So this is a graded C algebra. And furthermore, this ideal is left invariant under the action of the symmetric group. So I also have a graded Sn module. And if you want to know what it looks like, Chevalier gives you an answer, right? So the coinvariant ring Rn is isomorphic as an Sn module to the regular representation of Sn. And this is a very nice theorem, but the first time you see it, you might feel cheated somehow. We started with the symmetric group. We had the symmetric group act on a polynomial ring in an interesting way. We got rid of, well, basically the boring part of that action, and we just got back to the symmetric group. So what did we gain? And what we gained was graded structure, right? So we have a graded Sn module, and the graded isomorphism type of this Sn module was calculated by Lustig and Stanley. And here I'm stating this in the language of symmetric functions. So I'm representing a symmetric, in Sn irreducible with the corresponding Schur function. The graded character of Rn, where Q is my grading variable, can be expressed combinatorially as a sum over standard tableau within boxes of Q, my grading tracker, to the major index of that tableau. And now I have my stand-in really for the irreducible representation of Sn corresponding to the shape of my tableau. So we won't be talking so much about module structure in this talk today, but this is just a very kind of nice result that's inspired a lot of very cool mathematics. So what we will be talking about more is geometry. So we're gonna stick to type A today. And I'm gonna let G be the general linear group of n by n invertible complex matrices. And we'll think about the standard Borel subgroup of upper triangular matrices and the standard torus of diagonal matrices nested inside like that. And the flag variety can be thought of in two different ways. Either it's G mod B, or you can think about it as the collection of nested chains V dot of subspaces inside Cn, where I have one subspace for each dimension. Okay, so this is the type A flag variety. We can endow this thing with the structure of an algebraic variety. And we can ask for its cohomology. So this was calculated by Borel, very famous presentation that the cohomology ring of the flag variety is equal to Rn, right? This is the coinvariant ring. And if you really want to know what's going on in this presentation, these variables xi are corresponding to Chern classes. So xi is, say, up to a minus sign, the Chern class of this tautological line bundle, vi mod vi minus 1. Okay, so this is the Borel presentation. It's presenting cohomology as a graded C algebra. And actually, it's also presenting cohomology as a graded SN module. So SN does not directly act on the flag variety as I presented it here. However, there's a construction due to Springer that says that SN does in fact act on cohomology, and that action agrees with the variable permuting action that you see on Rn. Okay, so this is the Borel presentation. So we want to talk about equivariant cohomology today, and I am perhaps the wrong person to try to give an exposition to this particular audience, but I'll try. So we'll talk about torus equivariant cohomology. So we're going to think about a rank K torus, C star to the K. That object is topologically a torus. And we're going to think about a contractible space, ET, which carries a free right action of T. So such a space, ET, can be constructed. These constructions are often quite painful, but as is so often the case in algebraic topology, you do the construction once and you can forget about it for most purposes later on. And really kind of the object of interest is going to be X. X is going to be a space that carries a left T action. And we're going to form this funny thing, this space, this fiber product of ET and X over T. So this is the Cartesian product of ET and S and X modulo this relation, right, involving the action of my torus. And if you've never seen this before, what you should think of is X mod T, right? So if I have a group acting on a set, it's very natural for me to consider the associated collection of orbits. And if I have a group acting on a space, I can form the associated quotient topology on the set of orbits. But if this group action isn't free, this quotient topology can be very badly behaved, right? So what I'm basically doing here is I'm taking my space X, I'm crossing it with this contractible space ET that is somehow topologically not doing anything. And the magic of this contractible space ET is it's somehow forcing this torus action to be free, right? So this is an approximation somehow of the quotient of X by the T action. And now we come to the definition of equivariant cohomology. So the equivariant cohomology of X with respect to T is the ordinary cohomology of this fiber product. And the way to think about this is it's an equivariant enhancement of ordinary cohomology. And a really cool feature of equivariant cohomology that will be important in this talk is that the canonical map from X to a single point, so I can let T act on a single point. This is an equivariant map. This turns my equivariant cohomology ring into a module over the equivariant cohomology of a point. And this module is in fact a polynomial ring. And here we have our first typo. This should be a polynomial ring of rank K, the same rank as the torus, not N. Sorry about that. So what does equivariant cohomology look like in the case of the flag variety? So first off, what's our torus action? So G mod B, this is the set of left cosets, G capital B. And we have an action of the torus on the left, looking like that, right? So our diagonal matrices are acting like so. And we can present we can understand the equivariant cohomology ring as a quotient ring. So this is this kind of presentation as a quotient ring is referred to as a Borel-style presentation. And we have a very nice answer here. So we have a polynomial ring and the n x variables that we saw before. And now we have n new t variables coming from the torus action. These are kind of called torus variables. Secretly, they're corresponding to certain Chern classes as well. So we have this polynomial ring, and now I'm modding out by this ideal where I look at differences of an elementary symmetric polynomial in the x's minus the same elementary symmetric polynomial in the t's, right? So that generates an ideal. And this is the cohomology presentation in the equivariant setting. So this is a Borel presentation. There's another kind of presentation of equivariant cohomology that's very important in combinatorics, known as a GKM presentation. And we'll get to that later on. And, as is so often the case, in algebraic combinatorics, Q analogs, things like that, how do you recover the classical object? How do you recover ordinary cohomology from equivariant? Well, you just set the t variables to 0, right? And you get back to the standard coinvariant ring. Okay, so that was kind of your first example of an equivariant cohomology ring presented. And now I want to talk about what might be a slightly different twist on this idea. And this twist is going to come from orbit harmonics. So what is orbit harmonics? So orbit harmonics is a machine, like any good machine. It has an input and it has an output. The input of orbit harmonics is going to be a finite locus of points, z, in an affine space. And I'm just going to take c to the n. We'll be kind of friendly in this talk. And here I've drawn C2, and I've drawn a locus Z consisting of 6 points. And this locus Z has a certain amount of symmetry to it. Like you might imagine, these 3 lines, reflections in those lines, is generating the symmetric group S3. And I at least attempted to draw my locus in such a way that it's invariant under those reflections. So that's the input, and the output is supposed to be a graded quotient, which I'm always going to call R of Z in this talk, of the polynomial ring and invariable. So I start with this ungraded object, this point locus, and I'm supposed to output a certain kind of graded quotient ring. And I've shown orbit harmonics as a cartoon here. You're supposed to think about this locus of points as linearly deforming in the sense of flat deformations to a typically non-reduced subscheme of Cn supported at the origin, right? So it's a certain kind of linear deformation. It's a certain kind of scheme theoretic limit. But what does this actually mean algebraically? Well, one thing that's always a good idea to do if you're looking at a variety is to look at the ideal of polynomials that vanish on that variety. So z is a locus of points. I of z will be the associated vanishing ideal. And then you want to look in classical algebraic geometry at the associated coordinate ring. So this is the polynomial ring and invariables modulo I of z. I'll call it C bracket C. That's the standard coordinate ring notation. And in general, there's a little bit of a notational conflict here because, on the one hand, C bracket Z, if Z is a set, is the vector space, the complex vector space with basis Z. But algebraically, this quotient is the set of all regular functions, of all polynomial functions on Z. But the wonderful thing is, because Z is finite, right? By Lagrange interpolation, I can actually realize any function on Z as the restriction of a polynomial. So we have, in this finite setting, an agreement between these two objects, right? And C bracket Z, this is not a graded quotient. It's an ungraded object, but there's a standard procedure in algebra to go from an inhomogeneous ideal to a homogeneous ideal. This is the associated graded ideal. So what I do is I look at all possible polynomials, at least all possible non-zero polynomials in my ideal, and I take the top degree homogeneous component of that polynomial. So I'm calling that tau of f, or a polynomial f. So this set of polynomials, this is a set of homogeneous polynomials. It generates by construction a homogeneous ideal. And the quotient of my original polynomial ring and invariables by this new homogeneous ideal, that this is what I'm calling the orbit harmonics quotient. So this is the procedure. Start with the point locus, look at the vanishing ideal, take the associated graded, take the quotient by the associated graded. And this orbit harmonics deformation, really what makes it work is that it has a certain amount of memory. So this non-reduced subscheme, this graded ring, it remembers to some degree where it came from. So although the coordinate ring of Z and R of Z are almost never going to be isomorphic as rings, right? One is reduced, one almost never is. We do have an isomorphism of complex vector spaces. So R of Z is going to have the same vector space dimension as the number of points. And not just that, if your locus was stable under the action of some group G, a finite matrix group, a linear group, you actually have an isomorphism of ungraded G modules, right? So the action of G on my locus of points is going to be isomorphic to the action of G on this quotient ring, but this quotient ring, we almost got something for nothing. It has this new graded structure, right? So this is the orbit harmonics deformation, and we're going to kind of jump into examples in a bit, but maybe I'll pause to see if there are questions. Okay. So I thought it would be good, if you haven't seen orbit harmonics before, just to work through one example of what this deformation looks like. So I've taken a locus of 3 points in C2, 1, 0, 0, 1, and 1, 1, like that. And the orbit harmonics deformation is supposed to be deforming these 3 points linearly to a subscheme supported at the origin. So let's say that we wanted to actually compute the graded ring that you get from orbit harmonics. Well, first off, what you do is you look at the vanishing ideal of these 3 points. And well, actually, whenever you have a finite set of points in Euclidean space inside C to the n, you can always express its vanishing ideal as an intersection like this, where, as you see, we have these point ideals here, and the coordinates in my point ideals are the same as the coordinates of my points. You can go to, say, Macaulay 2 to get generators of this intersection. In this particular case, they look like this. So this is an inhomogeneous ideal. And what you do is you take the top degree forms, right, of the generators that Macaulay 2 spat out for you. And these are going to be contained inside the associated graded ideal. And in fact, here, we're going to claim that we have an equality, right? So our associated graded ideal is supposed to be generated by x1 squared, x2 squared, x1, x2. And the way that you actually establish equality here, it's a little bit subtle, because even if I have a generating set of my ungraded ideal, the top degree forms of these generators are not usually enough, or not always going to be enough to generate my associated graded. But in this case, the quotient of my polynomial ring in two variables by these three polynomials is a three-dimensional vector space. 3 is the number of points, and therefore I did actually fill out my associated graded. This can also be done computationally. If you start with a Gröbner basis of I of z with respect to a graded term order, then the highest degree components will always be enough to generate the GR. And now we have our orbit harmonics quotient ring. C brackets x1, x2, modulo x1 squared, x2 squared, and x1, x2. We can look at this object in its various degrees. So in degree 1, we have a basis of the in degree 0, we have a basis of the constant polynomial 1. In degree 1, we have a basis of the variables x1, x2. And you'll notice that this locus is stable under an action of S2 that flips in the diagonal. In degree 0, we see the trivial representation. In degree 1, we see the defining representation of S2, right, acting on C2. And correspondingly in our locus, we kind of see this defining representation in these 2 points, this orbit of size 2, and we have 1 point on the line that's going to give us the trivial representation. So somehow this orbit harmonics deformation, it took this S2 module and it spread it out across 2 degrees like this. And the way it spread it out had everything to do with the precise alignment of these 3 points in the plane. Okay, so this slide is supposed to convince you that orbit harmonics is everywhere. So the name of the game here is you want to choose a locus Z, a point locus with some interesting organization. And if you do that, you might get a quotient ring R of Z that has some interesting properties. So first off, you might take a Weyl group W, acting on its reflection representation, and you might take Z to be a regular orbit of points, just one regular orbit of points in W. And it's a result of constant, and it's a little hard to trace, but this is certainly one of the first places where orbit harmonics appeared. It's a result of constant that the orbit harmonics ring R of Z is the cohomology ring of the associated flag variety G mod B. And we'll be talking about that in type A in a bit. Next up, you could, let's go back to type A. We'll take a single SN orbit of points, but maybe assume that some of the coordinates of your points coincide. So take an SN orbit that has a certain interesting stabilizer, S mu. So I have some points that live on some reflecting hyperplanes. It's a result of Otto-Springer, Tanasaki, and Garcia-Procesi kind of combining their work, that the associated orbit harmonics quotient is the cohomology ring of the type A Springer fiber attached to mu. So these were a couple of loci with, you might say, geometric organization or reflection group organization. You can also think about combinatorial organization. So you can fix n and k with k at most n, and you can consider a locus corresponding to ordered set partitions of the numbers between 1 and n with k blocks. So here I have the numbers between 1 and 6, and I have 3 blocks. So n is 6, k is 3. And you might object, well, this is not a point in Euclidean space, but you can sort of turn it into a point by letting the ith coordinate of your point basically measure which block I landed in, like so. So you get a locus of points. We'll talk more about this locus later. And the associated orbit harmonics ring turns out, by a result of mine with Jim Haglund and Mark Shimizono, to be a kind of co-invariant ring that you can attach to the delta conjecture of Haglund-Rummel-Wilson in some precise sense that I'd be happy to get into later. And maybe more interestingly for our purposes, it also presents the cohomology of a certain space X and K of spanning line configurations that I defined with Brendan Pulowski. And we'll be kind of going more into the details later on again. So I tried to focus a little bit on the cohomological applications of orbit harmonics. Cohomology rings are graded, so they might kind of come from this machine. But I just really want to say that there are a lot of other interesting graded rings in algebraic combinatorics, a lot of other combinatorial applications that arise from orbit harmonics if you choose the right point locus. So there are applications to Coxeter-Catalan theory in parking spaces that I developed with Drew Armstrong and Vic Reiner. There are applications to Donaldson-Thomas theory, calculating classical and quantum DT invariants for certain kinds of symmetric quivers. This was with Reinicke and Tuare. Nantel-Bergeron and Gagnon have a very interesting application to kind of a quasi-symmetric analog of the co-invariant ring. And there's an application to Ehrhart theory, or a graded analog of Ehrhart theory, that I developed with Vic Reiner, and there's more that I could say here, right? So a very ubiquitous kind of construction and combinatorial deformation theory. So what about this constant example? How can we talk about the cohomology ring of the flag variety with orbit harmonics? So I'm going to let alpha 1, alpha 2, up through alpha n be distinct complex parameters. And we're going to have a locus z, really z of alpha, depends on alpha. And it's going to be given by the set of points in C to the n of the form alpha w of 1 up through alpha w of n, where w is in Sn. So you take alpha 1, alpha 2 up through alpha n, you regard it as a point in n space, and you permute the coordinates around, right? So you have now n factorial points because you assume that the alpha I were distinct. And the observation that you can make I guess my slides are a little out of order. Sorry about that. The observation you can make is that if I start with a polynomial which is in fact symmetric, right, then f of x1, x2 up through xn minus f of alpha1, alpha2 up through alpha n is automatically going to vanish on my locus z of alpha, right? That's because, well, what it means to be symmetric is it doesn't matter in what order I plug in these arguments. It doesn't matter in what order I plug in the alpha I. And not just that, in fact, the vanishing ideal of z of alpha, this locus depending on alpha, is generated by the dth elementary symmetric polynomial in the x's minus the dth elementary symmetric polynomial in the alphas, where d ranges between 1 and n. It turns out you can show that the associated graded ideal of z of alpha is actually generated by these EDs. And the result of all of this is the presentation, or the result of all of this, sorry, is the type A coinvariant ring. So we see that the orbit harmonics ring for this particular locus, depending on alpha, is the type A coinvariant ring. This is due to Borel. And now what we're going to do is we're going to say that we'll take these alphas, we'll take these things that were just complex numbers, and we'll do kind of a mysterious thing. We'll replace the alphas with t's, right? So we'll say it's not going to be ed and alpha 1, alpha 2 up through alpha n anymore. It'll be ed and t1, t2 up through tn, right? So I'm going to look at this new ideal inside a polynomial ring and 2 times n variables generated by ed in the x's minus ed in the t's. And we get this kind of bizarre thing where when I replaced my alphas and I replaced my complex numbers and the orbit harmonics deformation with torus variables, and I looked at this new ideal, what I got was, well, the presentation of the equivariant cohomology ring. So ordinary orbit harmonics that was presenting ordinary cohomology, replacing my parameters with t's, was giving me equivariant cohomology. Okay. So that was a little weird. Let's see if we can get another example of this phenomenon. This next example is going to come from the theory of Springer fibers. So these are varieties that are indexed by partitions of n. So I'll let mu be a partition of n, a weakly decreasing sequence of positive integers summing to n. And I'm going to let x mu be a nilpotent n by n matrix of a Jordan type mu. So the Springer fiber associated to mu is a certain closed subvariety of the flag variety, B mu. And what is it? It's the set of all complete flags V dot in G mod B, such that X mu preserves my flag. So X mu of VI is a subset of VI for all I. Okay, so this is a closed condition. I have a closed subvariety called the Springer fiber. And we don't just want varieties, we want varieties with torus actions. So what kind of a torus acts on my Springer fiber? It's actually not the full torus of diagonal matrices, that this variety is not closed under that. However, we have an action of a certain subtorus. So I have my partition mu1, mu2, mu3, and so on. And I can think about the subtorus of my full diagonal torus, where the first mu1 entries are constant, the next mu2 entries are constant, and so on, right? And if I had a partition with k parts, what I have is a rank k torus acting on my Springer fiber. Okay, so what is the cohomology of the Springer fiber? How could we present it? So we're going to let mu have k parts, and there's a presentation of this cohomology ring that was due to Otto Springer, kind of cleaned up by Tanasaki, and this presentation involves a little bit of noise, a little bit of notation. So we have this k part partition, and if S is a positive integer, I'm going to let P sub mu of S be this thing. So what you do is you take the Young diagram of mu, you sort of throw away the first S rows, and you count up the number of boxes that remain. And also, if F is a symmetric polynomial and if S is a subset of my indices 1 through n, I'm just going to let f of s be the evaluation of f at the variables indexed by s. And this is the presentation of the cohomology of the Springer fiber due to Springer and Tanasaki. So this presentation is, again, a quotient of a polynomial ring and invariables by a certain ideal I of mu, where I of mu is generated by certain partial or certain elementary symmetric polynomials evaluated on partial variable sets, right? So we have elementary symmetric polynomials ED evaluated on, well, subsets S of my invariables, where the degrees and the sizes of my subsets have to obey a certain condition that I can never quite remember, but I've written down here. So that's the cohomology. And how could we connect this with orbit harmonics? So now we kind of throw in this work of Garcia-Procesi. So we have this partition mu with k parts, and Garcia-Procesi built on the work of Springer and Tanasaki to show that the cohomology ring of B mu is the orbit harmonics ring attached to a certain locus, z mu alpha. And what's z mu alpha? Well, we're going to let alpha 1, alpha 2 up through alpha k be distinct complex parameters. And we're going to look at the set of points in C to the n, where my point z1, z2 up through zn has to have mu I copies of alpha I, right? So I've drawn an example here, z2, 1 of alpha. The idea is I have to have 2 alpha 1s, 1 alpha 2, and there are 3 points in C3 that achieve that. So Garcia-Procesi showed that this orbit harmonics ring is equal to, well, in fact, the quotient presentation that you saw in the last slide. But what about equivariant cohomology? Well, kind of with our success with the classical flag variety, we might try to do something similar. Roughly speaking, we want to turn the alpha parameters into torus variables, and we'll be, well, maybe a little bit more sophisticated. So we have this rank k torus. We correspondingly have k distinct complex parameters. And we're going to think about these varieties, these z mu alphas, as fibers in a family, right? So I'm going to introduce a new locus. This will be an infinite locus, an infinite variety, z mu. So z mu is going to be living inside c to the n plus k, and it's the Zariski closure of this union. So I'm going to do a union over alpha and c to the k. Sorry about that. There should be a k, where the coordinates of the alpha have to be distinct, and I'll have z mu of alpha cross alpha, right? So I have this new variety z mu, and it's a theorem. It follows from a presentation of Hiraku Abe and Horiguchi that the torus-equivariant cohomology of my Springer fiber can be presented as a polynomial ring in n plus k variables modulo the vanishing ideal of this infinite Zariski closure. So again, we have this kind of strange coincidence where you get this equivariant cohomology Borel presentation from orbit harmonics by sending the alphas to t's.
Hi, Brendan. I have a quick question about sort of the citation of this result.
Yes.
There's a paper by Kumar and Procesi where they prove this presentation for Springer fiber. So I always thought it was due to Kumar and Procesi.
Thank you very much. So I am unaware of that paper. I noticed this paper of Abe and Horiguchi where they have a presentation that works in terms of orbit harmonics, but the paper of Kumar and Procesi, do you remember the year on that?
I think it's 2012 in its Journal of Algebra, I think.
Okay, yeah.
I can send you, I'll send you an email or a link it or
Thank you
something.
very much. Yeah, the Abe Horiguchi thing, that's 2014. So 2012
Okay.
was earlier than 2014, but
Right.
As I alluded to earlier, I am far from an equivariant cohomology expert, so any citation help you guys can provide would be very useful.
Sure. Yeah.
Thank you.
Mhm.
Okay. And now we're going to kind of get into kind of trying to formalize this orbit harmonics equivariant cohomology phenomenon. So phenomenon.
Brendon, maybe do you want to take a couple of minutes break?
Oh yeah. Actually, yeah. This is kind of a good time for maybe a 5-minute break. Yeah. Thank you.
All right. Okay.